So today we will talk about something which is more geometric in the nature. So for the first ground, you may think that it's quite different from the arithmetic setting that I have explained to you last week. But in the afternoon, we will explain the relation between these two models. So let me begin the third lecture. About the geometry of vector bundles of curves. So the first section is about some reminder on basic notion of vector bundles of curves. So we fix a field, a base field. Okay, and also we fix a regular projective curve, which is denoted by C. So just a small reminder by vector bundle of C. So we just mean a locally free sheaf of finite rank. So if the rank is 1, we just say that E is a line bundle. So of course this is rather algebraic point of view for theory of vector bundles. You have seen the notion of Arakelov degree for lattices or adelic vector bundle over Q. So here, for the setting of a vector bundle over curves, you also have a notion of degree. So I begin. So for the purpose of comparison, I would like to give you some definition which is similar to the arithmetic setting. So just first I give the geometric definition for a degree. So this is just the degree of the intersection cycle of the first term class of E with C. So then I will give you more arithmetic definition. So let C be a line bundle, let L be a line bundle on C. So it is an invertible sheaf because locally it's free of rank 1. So for any closed point, so Lx is just a free module of rank 1. So we can pick a generator. Of this free module of rank 1, which is denoted by Lx. And then if S is a rational section of L, so namely S is an element of L tensor OC of KC. So this is the field of rational functions on C. So S can be written in a form somehow like AX of LX. So of course this depends on S. So here AX of S is an element in K of C. So now the point is that OC X is a discrete variation ring with fraction field Kc. So you can talk about a discrete variation. So let Vx is the valuation corresponding to this variation ring. And then we define Vx of S just as a variation of this rational function Vx of Ax S. So if you change the generator, you just multiply Axs by some unit in the valuation ring, so it does not change the value. Variation of S. Now, what is the relation with the definition above? To say the degree of L is just something like a sum of x in C closed. So Vx of S times the degree of kx over k. So here S is some element in L tensor Kc, which is non-zero. So of course this definition does not depend on the choice of S, as you have seen. Yeah. So I need to say that for any k in Kc, f in Kc, which is non-zero, you have some sort of product formula. So which assure that this formula corresponding to degree of L does not depend on the choice of the non-zero rational section S. So for general, if you have a vector bundle, so you can consider the determinant vector line bundle, which is defined as X-tail product of exponent rank of E, the vector bundle E. Then you can you have some formulas. Degree of E is just the degree of this determinant. So you have some notions which are very similar to the case of adelic vector bundles over Q. You have also the notion of degree, which is also linked to the determinant of the vector bundle. So in the theory of vector So the notion of slopes and Hadana-Hashima filtrations is classically studied. So then I will give you some reminder of such construction. Let E be a non-zero vector bundle. On C. So the slope of E is just defined as the quotient of the degree of E over the rank.
What do you mean non-zero?
The rank is not zero. I mean, rank of E is positive. Otherwise, you cannot make the quotient. Some fundamental properties of degree and slopes. The first property is about the tensor product of two line bundles. So if L and M are two line bundles, and you compute the degree of the tensor product of L and M, you will find the sum of their degrees. So this is rather straightforward if you take the definition as above. So you have the tensor of two sections which are locally rational functions. And the valuation will transform the product to a sum. So you have this formula, degree of tensor product is the sum of the degree. And more generally, if E and F are vector bundles, so maybe non-zero vector bundles, so the slope of E tensor F is the slope of E plus the slope of F. This might take a little bit energy to prove it. So just you use the formula that the determinant of E tensor F so it's isomorphic to the determinant of E, but to some tensor power with exponent rank F, and the tensor determinant of F to some power rank E. So it comes from this relation. So the second property is that if you have a short exact sequence, vector bundles, then you have the degree of the middle vector bundle is the sum of the degree of the first and the third vector bundles. And this comes from the relation that the determinant of E is isomorphic to a determinant of F tensor the determinant of G. So if you apply the formula for calculating the degree, you find this. So the third property is that each E is a vector bundle of C. And you have two vector bundles, subbundles of E. Then you have the relation that the degree of E1 intersection with E2 and plus the degree of E1 plus E2 is bounded from below by degree of E1 plus degree of E2. So here E1 intersection with E2 is just the largest vector subbundle of E, which is simultaneously vector subbundles of E1 and E2. And the E1 plus E2 is the smallest vector subbundle of E, which includes E1 and E2 simultaneously. So, just one word about the idea of proof. So you would say that you have some exact sequence to some direct sum. So, but this is not exactly true in the level of vector bundle. Of course, if you take a generic fiber, if you take this one, so on KC, then this is a true exact sequence. Then you need to make some efforts on the comparison of OC module structure. So you have some vector bundle is included in some other one, and then you have some comparison on the degree. So, so the essential point is on generic fiber you have some exact sequence, and then you can compare the structure of OC modules. So I will not explain more details about this, but later, maybe next week, we will give some rigorous treatment in a more general setting. So I just avoid going into the details in this particular situation. So the fourth property is that so the degree of dual of some the vector bundle is just the minus degree of E. So again, you observe some similar situation to the lattice case. In the lattice case, if you compute the degree of the dual lattice, is minus degree of the initial lattice. So so now, in the last week, we have observed some more, how to say, some more invariants, except the degree or determinant of the lattice. So you have some first minimum and the last minimum. So the first vector that is non-zero, or the radius that you can find a basis of vector space inside the ball. So, of course, in the case of vector bundles, you can do some similar thing. But here, you have some algebraic structure of OC modules. So, sometimes it's more convenient to consider successive slopes than successive minima. Because in some sense, every closed points are considered in some equivalent way. So you don't have the distinguishment between Z module structure and the norm at the infinity. So in some sense, it's more convenient to consider more global invariants than successive minima. So I will give you a classical definition of successive slope of a vector bundle. So these are invariants which are finer than just the degree of the vector bundles. So let E be a vector bundle on C of a positive rank. So we define the maximal slope. E is the mu max of E, which is a superman of non-zero vector subbundles of E, and we compute the superman of the slopes for all non-zero vector subbundles of E. And also there is a dual notion given by the minimal slope of E as the mu mean E, which is infimum of so these are quotient bundles. Of course, G is also non-zero, and you compute the infimum of mu G for all quotient vector bundles of E. So last week we have observed some complex estimations of the sum of lambda max and lambda min of the dual lattice. So, but if you take the slopes as your favorite invariant, then in this sense the transference becomes very simple. So you just have a mu max of E plus mu min of E dual. So it's 0. So this relation comes from this point. If you take a degree of some dual, you find a minus degree. So if you take slope, so you have the same thing, and also this property. So if you have some exact sequence, and then the degree of the middle one is the sum of the first one and the last one. So the point is that if you have some vector subbundle of E, by quotient you obtain some quotient vector bundle. Then you can recover the degree of E as the sum of this one and this one. And conversely, if you have some quotient bundle, and then you have the kernel, which gives you this subbundle. And that is very important to give this property. And it is not that possible to have the similar thing of this statement for not for the degree of so not for the invariant of degree, but for successive minima. So that is not true. So in this sense, slopes behaves better in the point of view of geometry. Okay, so we say that E is semi-stable. So if the maximum slope of E is just the slope of E, so or equivalently, minimal slope of E is equal to the slope of E. So what is quite interesting for this feature is that so in some sense maximal slope is similar to the minus log of the minimal length of non-zero point in the lattice. So of course there is some advantage of such a definition of the minimal length is that you can pick some points in your lattice which gives you this minimal length. So here for maximal slope, so you can have some very similar situation in the sense that you can effectively find some universal vector subbundle which gives you the maximal slope. So let me state it as a theorem. So let E be a vector subbundle. So there exists a unique. So uniqueness is also a consequence of the properties of this universal vector subbundle. So unique E, so this subbundle of E so which satisfies following two properties. So first, this vector subbundle admits a mu max of E as its slope. So it attains the maximal points for this definition.
Which way, so let E be a vector bundle.
Vector bundle. Sorry. So of course we need to assume that the rank of E is positive. Thank you. So it gives the maximal slope of E. And what is interesting, more interesting, is in the second condition. So for any FE vector subbundle, such that the slope of F is also the maximal slope of E. So you will have the relation that F is also included in this universal vector subbundle. So therefore you observe the uniqueness by this universal property. So it includes every vector subbundle which realizes the maximal slope. So of course, if this one is not E, and then you know that your vector bundle is not smoothable. So so E ds is called the destabilizing subbundle. So in the sense that if so E is semi-stable. And only if this destabilizing vector subbundle is the same thing as E. And the consequence is that we can construct a flag, a filtration of vector bundle by using this destabilizing vector subbundles. So corollary. So we can construct a flag vector subbundles in a recursive way as follows. So you take E0 is 0, and then for I, which is at least 1, so EI over EI minus 1 is just given by E over EI minus 1, and destabilizing vector subbundle of this guy. And then so it's the only flag of vector bundle subbundles. E such that so first one, so each EI over EI minus 1 is semi-stable. So if you take this construction, you know immediately that this vector bundle is semi-stable, because if you take some subbundle, then its slope is bounded from above by the maximum slope of this one, which is the slope of this destabilizing vector bundle. So each subquotient is semi-stable. And the second condition is that you have the decreasing property for the successive slopes. So just a little remark is that this is just equal to the minimal slope of E, and this is equal to maximal slope of E. You make sense. So again, I will not explain the proof here. So in the end of the talk, I will explain the proof of this theorem in a more general setting. So I would like to leave as an exercise for proving the corollary. So by using the theorem here. Okay. So now again, exactly like in the arithmetic case, we can have an adelic view for the theory of vector bundles over curves. So that is the purpose of the series of talks, to put every thing which are apparently rather different into the same framework. So of course we needed to take some reference field. So this is just the field of a function, rational functions on C. And for any point x in C, which is closed point, so you will have an absolute value x. So from this field to these numbers, just the absolute value of f is exponential minus a degree of kx over k times the dx of f. This is an absolute value. So it is more or less like p-adic absolute value. So you have some valuation here corresponding to p-adic valuation. So there is a very typical situation is that here you don't have Archimedean places, you just have non-Archimedean absolute values. So sometimes this will simplify the treatment of arithmetic problems. So now if you have some vector bundle on C, then you have a norm on E tensor OC kx. So which is given by the norm of S is the infimum of the absolute value of AX. And the A is in K, kx, sorry, is 0, such that A minus 1 of S is in E tensor OC, and then O of kx. So this is the valuation ring of kx. So you know that this is an extension of OCX, which is the valuation ring of k with respect to this absolute value. So you have some OC module structure which permits you to construct some unit ball. And then if you know your unit ball, you know your norm. So that is exactly the same situation as in the lattice case. And then if you take this point of view, and then the degree of E is also given by minus of the sum for x in C closed. And then you take a log of the norm of S1, etc., Sn for this norm, for this determinant norm. So here Si is the basis. Of Ek. So if you have a basis of Ek, you can recompute the Arakelov degree like this. So of course, if A is just 1, so you have just some section, non-zero section, and you compute the minus sum of the log of the norm for this section. So you can observe that it corresponds to the initial construction. So finally, so we can recover other natural objects in terms of adelic setting. So if you, for example, if you want to determine the space of the global sections of vector bundle, So that is just a set of S in a generic fiber. So such that for any x in C closed, the norm of S on X is bounded from above by 1. So later we will use such thing in the arithmetic setting to study the global sections in arithmetic global sections. So so it's okay, you see it? Okay. So now, as I said, here we just have no-Archimedean places. We have a very nice algebraic structure, such as OX and OC module structure, so that this global section space becomes a vector space over K, small k, over the base field. So this is a very particular observation in the function field case. So you have some very nice algebraic structure. So that, for example, we can state a Riemann-Roch theorem, which is very neat. So you have some equality instead of inequalities, etc. So I will not talk about the proof for the Riemann-Roch theorem, but some consequences. So the reason is that so later you will see that such a definition is not not good for general adelic curves. So you need to find some an alternative definition in terms of the slope theory. So I will do it explicitly for curves, and then you will see that it's very natural to generalize it to a adelic curve setting. So I state the theorem of Riemann-Roch in a curve case. So let E be a vector bundle. And C. So you have H0 of E. So minus H0 so of E0 tensor OC, tensor omega C, sorry. So it's equal to the degree of E plus the rank of E, perhaps 1 minus T. So here H0 of something is dimension over the base field K of H0 C of something. And G is a genius. Okay. And omega C is a canonical bundle. So essentially it's to show that we find. So essentially this one is just H1 of E. Just one small remark is that the degree of omega C can be computed as G minus 2. Okay. So I will give you a series of consequences of this theorem. So let E the non-zero vector bundle. See? So first statement is that if the maximal slope of E is negative, then H0 of E is also is 0. Sorry. So if maximal slope of E is negative, you cannot find non-zero global sections. The second statement is that if the minimal slope of E is rather big, then H0 of E is the degree of E plus the rank of E times 1 minus Z. So, namely, you just don't have this term of H0 E dual times OC. And the third statement is that if mu mean of E is positive, so then you don't have the equality in general, but you have some estimate like H0 of E minus degree of E is bounded by rank of E times the absolute value of G minus 1. So you will have something which is less precise but similar in this type. H0 of E is not far away from the degree of E. And finally, so if you have E semi-stable of slope 0, then you have an upper bound of H0 by the rank. So H0 will not be very large. So, since I have not enough time, I will not give the details, but just explain orally the idea of proof. For example, the first statement. So, if you know that you have some non-zero section, the global section in E, that would produce some injective map from OC into your vector bundle E. So you can consider OC as a vector subbundle of E. And then you have some problem because OC is of degree 0 and of slope 0. So the maximal slope of E should be more or equal to 0. So that will contradict the assumption that mu max of E is is negative. And for the second statement, so if mu mean of E is greater than this one, you can compute mu max of E dual, mu max of E dual tensor OC, so which is mu max of E dual plus the degree of omega C. And then you know that the degree of omega C is 2G minus 2, and you know that mu max of this bundle is negative, and so H0 is 0, and you can have this equality. And for the third statement, you need to do some modification of your vector bundle, but the price to pay is that you would not have the equality, but rather inequality. So you need to twist E by some line bundle to obtain this inequality, of course by using this one. And finally, fourth statement is some inductive arguments on the rank of E. I will leave you this as an exercise. So these are not very complicated by using the Riemann-Roch theorem. So just some exercises. So now we will come to the alternative candidate for the H0. So the definition. So let E be a vector bundle on C. So it could be of rank 0. So we define a positive degree of E as follows. So degree plus of E, which is defined as the superman of F included in E. So superman for every vector subbundles of degree F. So this is necessarily non-negative because you can pick the zero vector subbundle. And if you compute the degree of the zero vector subbundle, it is 0. And therefore you always have 0 as in the set, so the superman should be non-negative. So of course if mu max of E is non-negative, then you have some comparison. Degree plus of E is bounded from above by mu max of E. So that is. I need to multiply it by the rank. Okay. So this condition is important because we pick superman for every vector subbundle, including 0. So even for the case where mu max of E is negative, such thing is always positive or 0. So only when mu max is positive, you have this comparison. And now with this notation, I can state a theorem that I will explain the proof in the follows. So if E is non-zero, vector bundle on C you will have the comparison as follows. H0 for E minus the degree plus of E is bounded from above by the rank of E times the max of G minus 1 and 1. So you can control the difference between H0 and the degree by the rank of E times this constant. So it is quite similar to this estimate, except that I changed a little bit the constant here. But here you have some extra condition that mu min is positive. But in this case, you have the equality between the degree of E and the degree plus of E. I will explain it a little bit later. Okay. Okay, so the idea of proof is to use the Hadana-Simon filtration that is explained here. So just some complement to this corollary is that you have some flag here. So this one is called the Hadana-Sima filtration. So I will explain the proof. So we pick this Hadana-Sima filtration. So let E equal to E0 and E1. And here Hadana-Sima filtration. E. So we also give some notation to such a successive slope for any I in 1 to n. Let mu I be the slope of ei over en minus 1. So of course you have mu1 more larger than mu2, etc. So let J be largest index, so max of I, such that mu I is positive or 0. So I will make a picture. So that is very classical in Hadana-Sima theory. Yeah. So rank of E1. So rank of E minus 1. Rank of E. So you can draw a picture like this. So if you take here the degree of E1. Maybe here degree of E2, etc. And then you find some concave function. And maybe here, so. So because the slope will decrease, so you find here the slope is mu1, and then here the slope is mu2, mu3, etc. So the slope will decrease. So you find some concave function which is defined on 0 to the rank of E. And then this J is just you count every slopes which are positive. So now you obtain some point here. So here is a rank of EJ. So here the slope is positive or 0, and then the next slope will be negative. So what you can say is that the point here is a maximal point of this function, concave function, because this is just the point where your slope changes the sign. Okay. So now, what is important in the theory of Hadana-Sima field theory is that so if you pick a point, general point of the form degree of rank of f, degree of f. So you pick one point, rank of f, of coordinate rank f, degree f. You pick a point like this. So the point always lie lie below this the graph of this concave function. So that is what you can say about Hadana-Sigma filtration. So that is a very important feature of this one. So therefore, we have such a claim. So claim 1 is that degree plus of E is the same claim of the degree of Ej. So because the degree of Ej, here the value here, so here the coordinate is rank of Ej, degree of Ej. So here the value is the maximal. It's the maximal value of this concave function. And for any vector subbundle f, if you draw the point rank f, degree f, your point lies below this graph. So degree f should be smaller than the degree of Ej. And therefore, degree of Ej would be a maximal degree. So the maximal degree can be computed using the Hadana-Sigma filtration. So, so of course I can give you a formal proof for this statement. So let EF be a vector subbundle so for any I let Fi be the intersection of F with EI. Then what you can say is that Fi over Fi minus 1 is a vector subbundle of EI over EI minus 1. So by this definition. And then you would have a slope of Fi over, so here Fi over Fi minus 1 may be 0, so I would like to say that degree of Fi over Fi minus 1 is bounded by a rank of Fi over Fi minus 1 times the maximal slope of Ei over Ei minus 1. But you know that Ei over Ei minus 1 is semi-stable. So its maximal slope is just its slope. So this is just a rank of Fi over Fi minus 1 times mu I. So mu I is the slope. So you can compute the degree of Fjf. So I've erased if you have some short exact sequence, you have some additive property for degree. So degree of f is degree of Fj. So minus the sum, plus the sum from I from j plus 1 to n, the degree of Fi over Fi minus 1. So this is bounded by a degree of Fj plus the sum for I equals to j plus 1 to n. So the rank of Fi over Fi minus 1 times mu I. So but for I from j plus 1 to n, all these mu i's are negative or 0 because j is the last index that the slope is positive and afterwards the slope becomes negative. So all these things should be negative or 0. So this is bounded by degree of Fj. So this is a formal proof, but it comes from this observation by graph that you would have such thing. So not only you have such a comparison, but also for H0 you have a similar comparison. So the second claim is that H0 of E is the same thing as H0 of EJ. So the proof is that so either you have E over EJ is 0, or you have the maximum slope of E over EJ is mu J plus 1 is negative. So this is because 0 equal to EJ over EJ included in EJ plus 1 over EJ, etc. E over EJ, so En over EJ, which is E over EJ. So if you pick this filtration, so this is the Hatana-Simon filtration of this vector bundle E over EJ. So you will have this observation. So if mu max is negative, then you find that H0 of E over EJ is 0. So in this situation, these two vector bundles are the same. So you have the equality between H0. So in this situation, you have H0 of this one is 0. Then what you can say, so you have some exact sequence. And therefore, you have a non-exact sequence of cohomologies. So and if this is 0, you do not have non-zero sections here. So you have an isomorphism between these two cohomology groups. So you have the equality. So anyway, you have equality. So these two claims allows to allows to prove the statement for the case where E is replaced by EJ. Okay, so now what is interesting is that if E is replaced by EJ, then the mu mean of EJ is positive or 0. Because the mu mean is last slope. If you stop at EJ, the last slope would be non-negative. So if the last slope is strictly positive, then you already have the comparison here. So this inequality is a little bit stronger. So it remains to treat the case where the minimal slope is 0. I will leave you it as an exercise. So you need to do a little bit stronger. So you need to reinforce a little bit this statement, replacing the positive here by positive or 0. As price to pay, you need to have a less stronger inequality here. But it's essentially the same thing. So what is different is lies here. So what is the difference? The difference between mu mean of E is positive and the mu mean of E is positive or 0 is that you have some subparts which are semi-stable of slope 0. So in this graph, you have some horizontal parts which can be decomposed into the pieces which are semi-stable of slope 0, and then you have some inequality here to make a bridge between these two situations. So I will leave you to complete the details. So this is very important because in general case we cannot use the definition of the classical case. So we need to use this degree plus to replace H0. So it's for this reason that I explain the details in the function field setting. So finally, I come back to the proof of the Hadamard-Hassiman theorem. So I would like to make a new statement, which is a formal one, which does not depend on the structure of vector bundles. So this theorem will be used later in the general setting. So in the literature there are many general Hadamard-Hassiman theory. So some in categorical setting, some other in the periodic representation setting, etc. So so I will explain some not so general theorem. So we fix a field K, any field. So if E is the vector bundle, in the vector space of a finite rank of K, we let theta of E be the vector spaces, be the set of vector subspaces E. And theta star of E is almost the same thing, but we don't consider the zero vector subspace. So definition, we call degree function. E, so any map V from theta E to 1 such that so for any E1 and the E2, which are vector subspaces of E, you have a degree of the E1 intersection with E2 plus degree of E1 plus E2, responded from below by degree of E1 plus degree of E2. So this is just the one of basic property of the degree function for vector bundles. So then if you have such thing, you got some slope function. Mu from theta star of E to R. So mu of f is just defined as the degree of f divided by rank of f. So you see, these are very general, very natural analog of degree and slope functions on vector bundles. Okay. So the theorem is that the first statement is that this slope function attains its maximal value the max or theta star E. And the second one, you can find some EDS in theta star E such that mu of EDS is mu max. And which contains f in theta star of E with mu of f equal to mu max. So you see, this is very similar to the theorem that I have stated. So in fact, you can, in some sense, use this statement to prove the situation in the same statement in the situation of vector bundles. So now we'll explain the proof of this theorem. So by induction, on n equal to rank H. So the case where rank is 1 is trivial, because in this case you have just 1 point in theta star of E. So they have a function on 1 point set. So it always attains a maximal value, and you have just 1. So in the following, so we assume that n is at least 2. So there is a trivial situation is that if mu of E is just the maximal value, then there is nothing to prove. Then the maximal value is attained, and EDS is just E. So the statement is true. So we can assume that there exists some E prime with mu of E prime strictly bigger than mu of E, and rank of E prime is maximal so among the rank of a subspaces of the slope bigger than slope of E. So these are some small argument to reduce the problem to this particular case. So of course, if the slope of everyone is not bigger than the slope of E, then you are in this situation. Okay. So of course, mu E prime is not E. So if mu E prime is E, then you would have mu of E prime is equal to mu of E. So that is not possible. So you have a rank of E prime is smaller than rank of E. So we can apply the induction hypothesis to E prime. So we can by considering a restriction of the degree function to a vector subspaces of E prime. So what is the induction hypothesis? Say so we can obtain the existence of some E prime ds, so such that mu of E prime ds is the maximal value of mu f for every f in theta star of E prime. So of course a priori this is smaller than theta star of E. Okay. And E ds prime include f once f belongs to theta star of E prime, and mu of f is equal to mu of E prime ds. So this is what the induction hypothesis tells you. So the conclusion is that actually you can take EDS is EDS prime to conclude the theorem. So we need to show that this one will satisfy the condition. So now I take some element in theta star of E. So if this f is included in E prime, then it belongs to theta star of E prime. So by the induction hypothesis, mu of f is bounded by mu of E prime ds, so which is E ds. So maybe I can remove prime because that's defined as this. So you have directed this inequality. So otherwise, your rank of f intersection with E prime. So f is not included inside. So this is smaller than rank of f. And so this will imply that the rank of f plus e prime will be bigger than rank of e prime. So it's all these two inequalities the consequences of f not included in e prime. Okay, so now f intersection with e prime is included in e prime. So this will. So maybe I just say that this ends. These are all conclusions of the hypothesis f is not included in e prime. So this f intersection with e prime is included in e prime. So you have mu of f intersection with e prime is bounded by mu of e ds because it's included in e prime. And then this rank is larger than rank of e prime. And this one will include e prime, and rank is larger. So we have to assume that rank of e prime is maximal among rank of subspaces of slope larger than mu of e. And then this rank is still larger than rank of e prime. So the slope of this one is bounded by the slope of e. And the slope of e is bounded strictly by slope of e prime. So that is the consequence of this comparison. Now we put all this estimates together inside so this such side of kind of condition. So you have a degree of f intersection with e prime plus a degree of f plus e prime is bounded from below by the degree of e prime plus the degree of f. And the slope of this one is bounded here, so it's bounded by mu of EDS, rank of f intersection with E prime, and the plus mu of E prime, rank of f plus E prime. So this inequality is strict because we have a strict inequality here. And then here you have a slope of E prime, rank of f, plus the slope of, E prime, plus the slope of f, rank of f. Okay. So now this would tells you that mu of f times the rank of f is bounded from above by mu of E prime, rank of f plus E prime minus rank of E prime, and plus mu of ds, EDS times rank of f intersection with E prime. But here you find this thing is just the rank of f minus the rank of the intersection. So this one is just this one. So so mu of E prime is bounded by mu of EDS. So this is bounded by mu of EDS times the rank of f. So you find that mu of f is strictly smaller than mu of EDS. So you have the first statement. So if you have equality, then the inequality strictly is not satisfied. So you are not in this situation, so you would be in this situation where f is included in E prime, so f is also included in E ds. So if you have equality but not inequality, then you have also this situation. So that shows that E ds satisfies the universal property. So thank you very much.
Do you have any question?
I have a question. How do we know that the EDS is unique?
Oh, so it will include every maximal point. And so it is maximal among vector subspaces attaining the maximal value of the slope. So maximal property shows that it is unique. So if you have two vector subspaces verifying the same condition, then one is included in another, another is included in one, so you have equality.